Alright, so in this video what I'm going to do is I'm going to first find the horizontal asymptote of the function f of x equals 3x times x minus 2 over x squared minus 4, and then I'm going to find the vertical asymptotes of the same function. So the first thing that I'm going to do is I am going to multiply the numerator. So I have then that 3x squared minus 6x is I'm sorry, minus 6x is being divided by x squared minus 4, right? And okay, so that's pretty good. And then what I'm going to do is I am going to take the limit of this. When you find horizontal asymptotes, you have to take the limit. Now I know that because the numerator in this expression here, in this rational expression, is of degree 2, and the denominator is of degree 2, that the limit of f of x as x approaches infinity is going to be equal to 3. So fact, okay, let me actually write that down. Since degree of numerator equals degree of denominator, right? We know that the limit of f of x as x approaches infinity is going to be the leading coefficient of the numerator over the leading coefficient of the denominator. Well, what is the leading coefficient of the numerator? It's going to be 3, and the leading coefficient of the denominator is going to be 2. I'm sorry, not 2, 1. It's going to be 1. Let me actually erase that. Sorry about that. Okay, so it's going to be 1. So I'm writing it over here. Okay, why not? So this is just going to be equal to 3. So therefore, I have to conclude then that the horizontal asymptote is y equals 2, 3. So that's the horizontal asymptote. And I have done that now. By the way, I should mention that if the degree of the numerator had been greater than the degree of the denominator, there would be no horizontal asymptotes. If the degree of the denominator were greater, okay, of the degree were greater than the degree of the numerator, then the horizontal asymptote would be the line y equals 0. I just wanted to mention that in case you get something like that. Okay, so next what I want to do is I want to compute the vertical asymptotes. Okay, and at the end of this presentation, what I'm going to do is I'm going to take you to Wolfram Alpha and look at a graph of this function to verify that we actually did the right asymptotes. Okay, so let me get started on the vertical asymptotes. So I have that f of x is equal to 3x times x minus 2. So y is equal to 3 times x minus 2, and the denominator of this is going to be equal to x squared minus 4. Okay. Alright, to compute the vertical asymptote. Okay, so to compute vertical asymptote. Okay, there may be more than one vertical asymptote. So what I need to do is I need to set the denominator equal to 0. So I have to find out where x squared minus 4 is equal to 0. So now this is going to imply that x, we have a difference of squares here, so we have x minus 2 times x plus 2 equals to 0. But notice what is happening over here. So this really what I have over here. Now you notice now why I actually left this expression, the numerator, as given, because now what I have is that 3 times x times x minus 2 is being divided by x minus 2 times x plus 2, and what is going to happen is that I am going to be able to cancel this here. So that means that this x minus 2 is not going to figure in my vertical asymptotes, only x plus 2. So now where's x plus 2 equals to 0? X plus 2 is going to be equal to 0 if I solve this equation, x equals to negative 2. So this is telling me that the vertical asymptote of this rational function here is at x equals to negative 2. All right, and at x equals 2, I don't have anything. Okay, this over here, my x minus 2 is equal to 0, and x equals to 2. So I don't have a vertical asymptote there. I only have actually a discontinuity, what they call a removable discontinuity, but I won't go into that at this juncture. All right, so now what I want to do is I want to graph this expression so that I can see if what I did is correct. And what I'm going to do is I'm going to go into Wolfram Alpha to check. Wolfram Alpha is a wonderful place to check things. It's good to do them by hand, and then you go there and check. Okay, so let me actually do that. Actually, before going to Wolfram Alpha, let me just remind you that if this expression over here had not been written in factored form in the numerator, when I actually computed the factorization of the denominator, I would have tested the values that I got where the denominator was equal to 0 and the numerator is, and if any of those values had turned the numerator into 0, I would have discarded those x values as possible vertical asymptotes. Just remember that. So you have to test, okay, your the zeros of your denominator in the numerator expression and see if you end up with a 0 in the numerator when you evaluate them for x. If so, you discard those x values as possible vertical asymptotes. Anyway, let me go to Wolfram Alpha and check. Okay, so here I am in Wolfram Alpha. I issue the command plot, and the expression was 3x times x minus 2. Notice that I use parentheses very freely here. This was divided by x squared minus 4, and I enclosed the whole thing in parentheses. Then I said that I wanted to see the graph, comma, from x equals to negative 5 to 5. So here it is. Wolfram Alpha has plotted this for me. Now if I notice over here, look at the graph over here. Okay, so let's look at the graph over here. So notice over here, this over here is the horizontal asymptote, and as you can see, it's approaching the line y equals to 1, 2, and 3. Okay, so that's the horizontal asymptote. Here I have the vertical asymptote, x equals to negative 2. So the horizontal asymptote was, again, let me repeat in case I said it incorrectly, it's y equals to 3. So is y equals to 3, and the vertical asymptote is x equals to negative 2. And if you notice here at x equals 2, I don't have a vertical asymptote, and that was because the numerator, when I evaluate at x equals 2, actually is 0 as well as the denominator, so I don't really have a vertical asymptote here. This is actually what they call a removable discontinuity, and of course it's not being shown here by Wolfram Alpha. Okay, so that's the way that we check using Wolfram Alpha, and it's really nice that we got to see this, because now I know that I didn't make a mistake in my calculations. Thank you for listening.